one specific extension of the Clapeyron equation is to a liquid-vapor equilibrium. So we're looking at the liquid-gas equilibrium. So the Clapeyron equation, again, is right dp dt. We're looking at the slope of the coexistence curve, pressure versus temperature. We get, if we're specifically looking at the liquid-gas equilibrium, we're thinking about vaporization. So we'll look at enthalpy of vaporization. We could write this in terms of entropy, but generally we think about things in terms of enthalpy. And then we have the change in the molar volume of gas versus liquid, right? So the delta V bar. Now there's an assumption we can make to simplify this expression. We can say, well, the molar volume of a gas is much, much bigger than the molar volume of a liquid. If you have 1 mole of gas, it takes up a very large volume, whereas 1 mole of liquid takes up a significantly less volume. And we can approximately say that it's so much bigger that if we take V bar gas minus V bar liquid, it's about equal to just V bar gas. That molar volume of the liquid is just not going to make a big difference. And so that allows us to simplify this expression to give the enthalpy of vaporization divided by the vaporization temperature times V bar gas. Okay, so that simplifies that nicely. The other thing we can do is we can assume ideal gas behavior. So if we ignore, right, if we are at sort of normal temperatures and pressures, this is a pretty good assumption. And so we can say that V bar for the gas follows the ideal gas law. So that'll be equal to RT over P. That's just solving for V divided by N. Okay, and we can make that substitution. So delta H for vaporization, the molar enthalpy of vaporization divided by T vaporization times RT, and we're going to be at that same temperature for this, divided by P. Or we can go ahead and collect the pressures together on one side of the equation and say we have 1 over P dP dt. So we just move this pressure over to the left-hand side of the equation is equal to the enthalpy of vaporization divided by RT squared. And we can rewrite this part on the left. We can either leave it like this or recognize that this is the same as the derivative of the natural log of P dt. That's the same thing. This is 1 over P is equal to the enthalpy of vaporization, again, molar value divided by RT squared. Right, and this equation here that we've gotten to, this is the Clausius-Clapeyron equation. And what this allows us to do is it allows us, and just as a reminder how we got here from the Clapeyron equation, there were 2 assumptions. We assumed that we have ideal gas behavior and that we can make this substitution for the, right, that the molar volume of the gas is so much larger than the molar volume of the liquid that we can ignore this difference. And this, both of these aren't possible when we're talking about the liquid and solid phase boundary, and so this equation doesn't work for that. This only works for gas, because obviously you can't assume ideal gas behavior for a liquid or a solid anyway. So that's sort of a moot point. Okay, now we can take this one step further. If we assume that the enthalpy of vaporization is constant with temperature, then we can go ahead and integrate this and get an integrated form of this equation. Okay, so we can integrate d log P dt from T1 to T2. Oh, sorry, we're integrating pressure. Sorry, this will go from P1 to P2. Will be equal to the integral of the enthalpy of vaporization divided by RT squared from T1 to T2. Okay, so on the left, we're going to get log P2 minus log P1, because we're integrating the derivative of the log, so we're going to get the natural log back. And that'll be equal to the negative delta H bar of vaporization over R times 1 over T2 minus 1 over T1. So this is an integral we've seen before in this class. All right, and this allows us, if we know the enthalpy of vaporization and, say, the vapor pressure at a particular pressure, one of the vapor pressures at a particular temperature, we can find it at a different temperature. And so in the next video, we'll look at an example of this.